Okay, so let's get started. Welcome to the live session of the Future Learn course Mystery of the Universe. Welcome, everybody. Today we have a guest, Daryl Santos from Germany. Hello, Peter. Peter, thank you for joining.
Hello.
Uh, so today I'm Tomo Goto. I'm an astronomy professor at National Tsinghua University in Taiwan. And then today we have a very good opportunity to interview my former student, Daryl Santos. He's actually now it's a PhD student at Max Planck Institute, right?
Yes.
Okay, I think he's going to introduce himself in a minute, but he was a student here at National Tsinghua University in Taiwan, and he moved on to a PhD course in Germany. So I hope we can hear a lot of interesting stories about Germany and also about Taiwan, astronomy research, life for astronomers, things like that. Okay. And then today we also have a guest, Professor Hashimoto from National Johnson University, also in Taiwan. When Dai was in Taiwan, Professor Hashimoto also worked with Dai. So hello, Professor Hashimoto.
Hello, nice to meet you, everyone.
Okay, okay,
I'm Tetsuya. Thank you very much for introducing.
okay. Okay, so let's get started. So Da, it's great to see you again. Can you briefly introduce yourself?
Yes, of course. I'll just share my screen.
Okay. Oh, very
Do you
well
see it
prepared.
now? I hope you're seeing my screen now. So,
And then Peter and everyone, you're welcome to ask questions at any time because we have plenty of time. Sorry, Da, please go ahead.
no, it's fine. Thank you so much. Again, thank you again for the introduction. And as Thomasan said, I am his previous student at National Tsinghua University. And as you can see here, this picture of mine is actually my picture when I graduated, when I finished my master's degree in Taiwan.
Looks very
So,
good.
yeah, thank you. My name is Daryl Joe Santos. My friends call me that. That's my nickname. And I would like to introduce myself by showing you a world map.
Mhm.
So here I want to briefly show you how I traveled across different countries for my academic journey rather. So I finished my bachelor's at Daryls University in Manila. So it's one of the top universities in the Philippines that focuses on research. And I finished my bachelor's degree in physics with specialization in material science. And I was working on some batteries, particularly in magnesium-based battery system for my research back in undergrad. And
Interesting.
then, mm, and then I had a jump. I switched to astronomy,
Mhm.
and I was quite brave and spontaneous to move to Taiwan and pursue masters in astronomy at National Tsinghua University. And that's
Okay.
where I met Tomo-san and then the Tsuya-san and then all his group members in his observational cosmology group. And then I went all the way to Germany
Mhm.
to pursue my PhD in astrophysics at Max Planck Institute for Extraterrestrial Physics. I am currently under the infrared group at MPE, under the supervision of Reinhard Genzel. If you know him, he's the 2018 Nobel Prize winner for his, together with Andrea Guess, for their observations of the Sagittarius A star, which is the black hole in the center of our Milky Way.
Mm.
So here's a picture of the PhD students batch 2021 to 2024. And I'm
Mhm.
not sure if you can see me there, but
Okay. Okay.
I'm somewhere behind. And then if you look a little closely, you'll see that there are international students. We're really diverse, you know. We come from different countries.
Right.
Um, mm. But Germans are actually minorities in the institute, and so are the PhD students. So, if I remember correctly, we are like around 30 in our batch, and there are like only three Germans. The rest are from all around the world, from France, from Netherlands, from India, China, and also in the Philippines. I'm the only
You said
Filipino in
only
our batch.
three out of 13 students are German.
Yeah, 3 out of 30, so that's 10%. So,
Oh, okay.
mm.
That's very small fraction.
and that's not including like the whole population, including scientists, staff. Like Germans are almost minorities in
Hmm.
the institute.
That's a quite difference from Taiwan because in
Hmm.
Taiwan, most students are Taiwanese.
Yes, yes,
In PhD course, there's some foreign students, but still, I think majority are Taiwanese students.
yes. Yes. Actually, that's what I want to emphasize later. If we try to compare the research environments in the different countries I've been into,
Hmm.
so yeah, that's like one of the major differences. Um,
Hmm.
yeah. So
We are actually trying to improve the situation, and then that's why we recruited you from Philippines.
yes,
If you remember, I think some professors went to Philippines to recruit some good students, and then Dao was one of the best students in Philippines. So we tried to convince him to come to Taiwan. That's how Dao came to Taiwan, I believe.
no, I think I just really grabbed the opportunity when they came into my university that time. So
Mm,
yeah, that's actually like a special case in my side because I didn't go through the normal application process because the representatives from the university, as Thomason said, went
mm,
into my university to advertise their programs. And then I was just there listening, and then I told them I'm interested. And
mm,
so I went to the interview process immediately, waited for them to send me my results, and then I got accepted. So that's where it all started.
mm. That's also good for Taiwanese students here too, to invite good, talented international people, and we can work together. We can collaborate. That's very beneficial for Taiwanese students as well.
Yes, you're right, Thomasan.
Mm.
Um, if there are no more questions, I'll proceed to my research.
Yes, yes, that's what I was going to ask.
Yes, because I believe Thomasan has already mentioned that I am working on black holes
Right?
for my research.
Mhm.
It all started with Thomasan start allowing me to study statistics of black holes, particularly
Mm.
the gas somehow change depending whether they are in a field environment, that is if they just live alone, if they're isolated, or if they're in a cluster, if there are many surrounding galaxies.
Mm.
And so that's what I wanted to investigate in my master's. But in my PhD, my focus is observations of black holes with
Mm.
gravity. So
Okay.
I highlighted three terms here. So when we say observations, I actually really go into telescopes
Oh.
to observe and use the state of the art instruments that are available to us to observe these black holes. Here's some pictures I took when I was in La Silla Observatory in Chile.
Oh.
That was September last year.
Mm.
Yeah.
Very recently.
So very recent, yes. And it was actually my first time doing observations by my own because I went there alone. And then
Okay.
some of my postdocs helped me online. So
Mm.
we connected via Zoom, and then they were helping me to navigate the whole process of observing uh, in
Which
real time.
telescope did you use?
We utilized SOFI.
Okay.
That's an acronym for Son of Isaac. If you can search it online, SOFI is an infrared imager and spectrograph. Basically, we used SOFI to take spectrographs. So we are trying to get spectra of the nuclear region, the center of the galaxies that we are interested in.
This is NTT telescope, right?
Yes, you're correct.
So
NTT telescope.
That is what is it? 3.5 meter new technology telescope, right?
Yes, you're right. 3.5 meters. Yes.
Okay. So Sophie is the spectrograph on this 3.5 meter telescope in Lasila observatory.
Yes, that's correct. I believe they have other spectrographs, but SOFI is what we used because it operates in the infrared region.
Okay.
And at around 2 to 2.4 microns.
Okay.
So this region is what we are interested in because, as I will say later, we are mainly focusing on the infrared region.
Okay.
Yeah.
So what were you observing again?
So we are observing black holes, particularly AGNs. So that's what I'm about to show you now. So AGNs are short for active galactic nuclei. So these black holes are in the center of the galaxies. And we call them active because they are actively accreting, or in layman's terms, they're actively collecting materials within their vicinity. And that gives them this accretion disk that we are seeing in this M87 picture. You see here this ring here.
Yes.
So this is the accretion disk that we are seeing here in this picture. And it's because it's active, that's why we see it. And these AGNs are powered, or there are manifestations of the accretion of supermassive black holes in the center of galaxies. So these SMBHs, that's their acronyms. So basically we believe that they are the center of most galaxies. So for instance, M87, as you see here, and they have several properties. As you can see in the upper picture, it releases jets. So that's one of the properties of an active black hole.
What was the purpose of your observation?
Okay, that's an interesting question because although we know that actually before the EHT images were released, like for M87, the existence of black holes in the center of galaxies was still a theory that we just believed. Based on the signatures that we have observed from the telescopes that we use. However, because of the latest technology that we have finally proven that there are really black holes in the center of galaxies. But there are still mysteries surrounding, for instance, how they grow. So how do these active galactic nuclei grow with respect to their host galaxies? We see, based from previous studies, that there are connections between the growth of the host galaxy and their central black hole. So we call this black hole galaxy coevolution. And by studying these black holes at very small scales, we can greatly look into smaller scales rather, of the black hole's structure, and to further shed light to this black hole galaxy coevolution scenario.
Can I ask a question here?
Please.
Sure.
These active galactic nuclei, are they the same as what we understand as quasars, or is there a difference between them?
Oh, yes. Quasars are actually types, another type of AGN. Because quasars, they are so very active to the point that the light from the AGN is too much. It's overpowering, or it's dominating the light from the galaxy. So what happens is that instead of seeing a galaxy, you're seeing like a star, quote unquote, but it's actually a quasar. It's an AGN that is accreting too much. It has very high activity. So yeah, in short, quasars are just a type of AGN.
Oh,
Thank you.
thank you, Peter, for a good question. May I also ask a question? So in your black hole pictures, the black holes are actually bright. Why they are not black, but it's emitting the light?
Yes. So here in this picture, for instance, M87, the black hole is actually in this dark region at the center of the this bright ring here. So this
Okay.
bright ring here is the accretion disk,
Okay.
but this whole black region here is the event horizon of the black hole. If you recall, the event horizon, that is the region from the black hole where light couldn't escape. So that's why it's black here. So
Okay.
we're not really actually seeing the black hole here. It's more of like the shadow of the black hole manifested as the event horizon. So we cannot really see the black hole here. And on top, it's just an impression from an artist. So the black hole is supposed to be
picture. Okay.
yeah, this bulge here. So yeah.
Okay. Thank you. Thank you.
Mm-hmm.
So how was your observation? Was it successful? Did you have the picture looks like you had good weather?
Okay, so actually it was really tricky because in this picture, if you see, the sky was very okay.
Yeah,
But
it looks nice.
during
There's
the
no
night
cloud.
it was not. So it was really difficult because September in Chile is actually a windy day.
Okay.
So we are plagued by winds, very high winds, and thick clouds.
Okay.
So during our observations, we unfortunately got just a few spectra of objects, but it's okay because it's just one of our observations with Sophie. So we had further observations last November, and then there's another one next February, so next month. So we are still looking forward to getting more data in the future.
Okay. Okay. Yeah, I know that when the wind is too large, too strong, you cannot open the telescope, right?
Yes, you're right.
Okay.
So going forward,
Yes.
we still have one more word here to define. That's gravity.
Okay.
So gravity in this picture is actually a second generation instrument at the VLT. So here's the Very Large Telescope. And then there are 4 UTs. We call them unit telescopes.
Okay.
And then what gravity does is that it combines the light from these 4 UTs. And then as it combines the light, we perform interferometry. So that's a process wherein we analyze the signals from the interference of the waves coming from these unit telescopes. And this
okay. You're going too fast.
okay, sure.
How big are these telescopes?
If my memory is correct, they should be around 8.4 meters.
Okay.
So,
So it's bigger than NTT telescope that you use.
Yes, it is. It is.
And there are 4 of them.
There are 4 of them.
Okay.
And if you have 2 telescopes,
yes,
observing the same object together, and then they are positioned within a distance,
yes,
then you can perform interferometry.
Okay. What is
then
that?
Interferometry is a method wherein we utilize the interference of waves coming
Okay.
from a source, And then, as you can see in this animation on the left,
Okay.
you see here the beam splitter. Sorry, the GIF is cut, but when the light is split into two different paths, and
Okay.
then they get combined again,
Mhm.
the way they are combined produces patterns.
Okay.
And these patterns we analyze to measure properties of objects such as the size, the shape, the astrometry or the position of the object.
Mm.
So this is what interferometry is.
So you combine the light coming into four telescope into
Yes.
one. Okay. And
Yes.
what's the benefit of this combining? You get more light?
Yes. Aside from getting more light, because there are four telescopes,
right?
Going back, there are four telescopes,
Mm.
and then you get a pair.
Okay.
So basically, you have 6 pairs.
Oh, okay. Four of them. So 6 pairs. Okay.
Yes, 6
I
pairs.
see.
And then we also use the rotation of the Earth to increase the coverage of these 4 telescopes. Because of course the Earth is rotating, so the telescopes somehow move with respect to the object.
Okay.
And so this increases the coverage of the telescopes.
Okay.
And this means we can get a bigger picture of what object we are observing.
Oh, okay.
Mm-hmm.
Well, I heard that the telescope's angular resolution becomes better with the size of your telescope. You know, the bigger
Yes.
telescope can resolve more tinier structure. And then
Yes.
by combining 4 telescopes interferometry, then you can resolve it's like a fake big telescope. So you can resolve more tinier structures. So you can see tinier things, I think.
Yes, thank you, Thomas-san. That is actually correct because I'm not sure if you're familiar with angular resolution, but for those who don't know, angular resolution tells you the smallest possible scale that you can measure with a
Okay.
telescope. And the formula is quite simple. It's actually the wavelength divided by the diameter of the telescope.
Okay.
But if you have 2 telescopes, the effective diameter that you need in this formula is actually the distance between these 2 telescopes. We call this the baseline of these pair of telescopes. And the formula, because it's the wavelength divided by the diameter, it becomes the wavelength where it operates, divided by the baseline. And the baseline is usually in kilometer scale. So the tendency is you get a much smaller value of angular resolution, and therefore that is the smallest scale that you can observe with your in this case interferometer. So that's why if you have larger baselines, you get higher angular resolution and therefore sharper images and higher resolution of images.
Well, what's the largest separation of these 4 telescopes? How long?
Actually, I don't have the numbers in my head right now, but I know the angular resolution of gravity. It's around 10 micro arc seconds. It's actually very small. If based from the fringes that we see, the high precision of gravity around 10 micro arc seconds, and it operates at near infrared wavelengths around 2 microns. This allows us to observe even the smallest parts of the AGNs. For instance, we focus on this region around the black hole.
Okay.
This is called the broad line region. And that's a very small. It's around scales of milliarcseconds with respect to the dust surrounding the black hole. So that's why, because of gravity, we are lucky that we can observe black holes and even focus on the smallest regions around the vicinity of black holes with gravity.
So no other telescopes can see this, but only gravity can see such a tiny structure.
Yes, you're right. It's world class. The only instrument that can do such science.
So gravity is actually the name of the instrument, isn't it?
Yes.
Does it have anything to do with the Einstein's gravity? It's just a name?
No. Gravity is actually short for general relativity something. I actually forgot because I'm used to calling it gravity, but it is actually an acronym.
Okay.
And the reason why is because the main purpose of this instrument is to test general relativity theory.
Okay.
And yes, and
So it
then
is related.
and then this study on AGNs is actually just one part of it. Gravity also conducts other sciences such as observing Sagittarius A star.
Okay.
So that is as I mentioned, the black hole in the center of our galaxy. And there's a dedicated team of scientists at MPE and also in other parts of the world that are focusing on observing the field around Sagittarius A star with gravity. And by observing these fields, they can measure the position of the stars around Sagittarius A star with high precision. And they measure it every 2 months, and then they can see whether the orbits of the stars change every month.
Okay.
And then they can check the effect of precession. So precession is the wobbling of the axis of rotation of an object. So basically, I don't have a picture with me right now, but when there is precession, the tendency of the orbit of the star around the black hole is to move a little bit compared to what we expect.
Okay.
And because of gravity's high precision, we can measure the position of the stars with high precision. So we can actually show that precession is actually happening in these stars. So if you're interested, you can search online about our results, gravity observations of Sagittarius A star.
Okay. Oh, sounds very interesting. So your PhD thesis project is also involved with this gravity instrument?
Yes, you're right. My PhD work focuses on the black hole part of AGNs. So as I mentioned, there are many sciences with gravity. They measure or observe the Sagittarius A star. They measure young stellar objects. They measure exoplanets. They measure what else? Black holes. And I'm in the black hole part of gravity. So I am working closely with Taro Shimizu for observing the black holes in the center of galaxies at the local universe. So around redshift 0.2. And hopefully, in the next improvements of gravity, which we call gravity plus, we can further increase the distance of the observed AGNs from the local universe 2 redshift around 1 or 2. So we can hopefully increase the number of objects that we can observe in the near future.
What is this gravity plus? Are you going to add more telescopes or?
Yes. So Gravity Plus will not really actually increase the number of telescopes, but instead apply more improvements on the telescopes.
Okay.
And this includes the separation needed between a star and the object. So in our observations, this is quite complicated, but I will just say that for every object we observe with gravity, we need a reference star.
Right.
Because this reference star is what we observe for atmospheric corrections. And then these atmospheric corrections we apply to our object. Currently, the separation needed, if I recall correctly, between the star and the object is around 15 arc seconds.
Okay.
But with Gravity Plus, we can increase this further to 45 arc seconds.
Okay.
And so this means there would be a lot more objects to be observed because the distance requirement is much larger.
Okay.
And so that's one thing. And then another thing is the improvement of adaptive optics in each of the telescopes. So adaptive optics, this is a term that we use. This is the application of atmospheric correction in real time.
Okay.
So basically, the light coming from the object that is corrected by removing the atmospheric effect. And that is in real time. So basically, the mirrors are deformed so that it somehow matches the waveform received by the telescopes. So that is adaptive optics.
Can I ask a question here?
Please,
yes.
Go ahead.
I understand that the James Webb Space Telescope also specializes in the infrared part of the spectrum, and that doesn't have the problem with these optics. So how does gravity compare with the James Webb Space Telescope?
That's a good question.
Excellent question.
Yes. The main difference between JWST and gravity is that gravity operates on ground, so in the Earth, whereas JWST operates in space. And actually, in space, you don't have these atmospheric effects. So they actually don't need adaptive optics to overcome this atmospheric correction because it's not affected by the atmosphere at all. Whereas with gravity and other ground-based telescopes, they have certain protocol for atmospheric correction. One way to do this is with adaptive optics, and that's what gravity is using. So I think that's the main difference between these two.
If I could add a little bit,
yes.
JWST has a 6.5 meter mirror. So it has a very large correcting area in space. So that's excellent telescope. But then this 6.5 meter of diameter is going to decide the resolution, how tinier you see the structure. But instead, the gravity, because by combining the 4 telescopes, the largest separation of the pair is 130 meter.
Thank you.
So it's like by combining 4 telescopes, you are creating 130 meter telescopes resolution. And then 130 meter is about 20 times larger than 6.5 meter, right?
Yes.
So the resolution of the telescope is 20 times better for gravity because its baseline is 20 times larger. So that's another difference between JWST and then gravity. So if you want to see a very tiny structure inside the black hole or inside AGN, or near the black hole, then gravity would be better than JWST because it has better resolution.
Yes, thank you, Thomas. You're definitely correct. Yes.
Peter, is that okay? Does that answer your question?
Yes, thank you. I was just wondering.
That's an excellent
how
question.
is gravity better than JWST, or how does it differ, or does it deal with a different wavelength, or exactly what is the difference in practice?
That's an excellent question.
Mm.
I would say both telescopes have, advantage and disadvantage.
Yes.
So.
Yes, and they do different sciences as well. So
right.
Different telescopes view different objects in different ways, and so this gives us a better picture of what the objects are. So it would be nice to combine the results from JWST
Absolutely.
and also with gravity,
right.
and see and compare what we can what results we can have from these telescopes.
Okay. Any more questions about DAR's current research? I hope. Okay.
Sorry.
Professor Hashimoto, go ahead.
Thank you very much. Maybe I just missed this part, but this gravity can resolve very tiny structure of the AGN. And then if you can observe this tiny structure inside this AGN, then what you can do better? So what you can estimate better? For example, you can estimate the black hole mass in a better way.
Yes, you're correct. For instance, measuring black hole masses has been a very important method in understanding the black hole galaxy coevolution scenario. That's because mass is a fundamental quantity. And so there are many ways to measure black hole masses, but with gravity, we can at least have a direct observation of the black hole in the center of galaxy, and therefore get a direct measurement of the black hole mass. And another quantity that we can measure is, for instance, the radius of the broadline region shown in this picture, and also the position of the BLR with respect to the black hole. So something like the angles, and also an isotropies in the BLR. Is it shaped like a disc, or is it shaped more of like a big chubby torus, or is it shaped like a clumpy torus, or is it like what do you call this? Is it illuminated on one side only, or is it illuminated on both sides? So these kinds of properties of the BLR we can also measure with gravity.
So therefore, in future, if you construct this gravity plus,
yes,
and maybe you can increase a lot of samples that you can precisely measure the black hole mass.
Yes, definitely correct. We would increase the possible number of samples or objects observed by gravity by around 100 times. So with gravity plus, so this would definitely give us a better picture of this coevolution scenario up to high redshifts at redshift 2. So we're looking forward to using Gravity Plus in the near future.
Oh, thank you very much. That's exciting. Thank you very much.
How much, I'm curious, how much does it cost to build this gravity instrument?
Oh my gosh.
It must be expensive, no?
Yeah, that is expensive. I don't have the numbers right now, but it must have costed 100,000 euros.
Oh, okay.
Or like €1 million, if I recall.
Okay.
I don't know how to convert that to US or to NTD. So.
Oh. Okay.
That must be expensive. But if we talk about the price, maybe there is also operation fee. No? Say
Of course,
you are
yes.
using the whole largest telescope in the world, right?
Yes,
That also must be expensive.
must be. And then the gravity team is quite large in Paranal in Chile. I've never met them, but I know they're a big group, so I think the operational costs must also be high.
Oh, okay, okay. Are there any more research questions? Ah, I see Albina is joining. Welcome, Albina. If there are no more research questions, I want to turn the subject and then
Yes.
ask about how's research life in Germany? How's it? Could
Okay.
you share your experience with us?
So I'll briefly show some comparisons between Philippines, Taiwan, and
That would be
Germany.
wonderful. That would be excellent. Thank you. Thank you.
So in the Philippines, unfortunately, I think that the research environment in Philippines is still in its infancy, since there are only a few Philippine universities that focus on research. My university is one of them, De La Salle University.
Okay.
And it would be nice to integrate some improvements in the science and technology environment so that it could be greatly improved in the future. Back then, I was working in the lab, so my research was hampered mostly by unavailability of reagents and equipment.
Okay.
So I think that that must be greatly improved in the future.
Well, at this time, you are doing a research on batteries, right?
Yes, at that point.
Okay.
But thanks to some connections in other universities, we were able to finish my research on time. So
Good. The
So-
picture looks very nice. You look
Yes.
like a doctor.
Yes. Basically, we took this when I and my group mates, my lab mates rather, took a picture outside my university. So
Good.
we are required to wear lab gowns.
And
But
then,
in Taiwan and Germany, when I jumped to astronomy, I didn't need to wear lab gowns anymore. I was more in front of the computer. So what's good with Taiwan is that there are lots of conferences locally and internationally. So I had lots of opportunities to join my group outside NTHU, joining conferences here and there, presenting posters, which helped me somehow improve my interpersonal skills and how to present my research in a diverse group of people. And then there's also this Asian culture of fondness among group members, which I really treasure and cherish because we're really close in our group. I mean, up until now, I'm still in touch with Tomo-san, who's my previous advisor. And last thing is that the Taiwanese government is really focusing on research to the point that they fund certain projects, and that's where we get our salaries for our research.
Well, that's true. If I can add a little bit,
Yes.
we have within Taiwan, we have physics meetings once a year, and then Taiwan astronomy meeting once a year. So my group and the students, we would usually go to conferences at least twice a year within Taiwan. And in addition, sometimes we organize international conferences. Actually, Professor Hashimoto is organizing an international conference next month. So we go there. But I'm a little bit sorry that our funding is not so small, but not big enough for to take all the students to oversee conferences. So I feel sorry about these points. If possible, I want to take all the students at least once to international conference outside of Taiwan, but funding is not enough to do that. So that part, I feel a little bit sorry.
Yeah.
Now, how's the situation in Germany?
Yes. So in Germany, I think Thomason, if you remember, Thomason mentioned about international students being few in Taiwan. This is completely different in Germany because researchers are from all around the world.
Right, yeah.
Yes. And then we have, I think, many facilities that are conducive to research. So here's a picture of me working with my laptop and my big computer, and I have lots of papers in front of me.
And you have a water bottle in front of you.
Yes.
Like a typical Taiwanese student. Taiwanese students always have a water bottle.
A water bottle. Yes, so we have lots of supercomputers also in our institute. So we get to work on our programming and codes with high speed. And in Germany, actually, and also in Europe, we emphasize work-life balance. So, for instance, we hold parties for PhD students like this. Actually, I'm one of the organizers for these parties, for this party, and then I took pictures. And on weekends, Germans really emphasize the importance of taking a break, having rest during the weekends, especially on Sundays. Like Sunday is family day. But in this case, I'm alone in Germany. I don't have my family, so I go out with my friends, go out and eat, watch something together in the theaters, or go around Germany. So work-life balance is highly prioritized here in Germany.
Oh, so these parties are organized by students? Okay.
It's organized by the students, for the students, and by the students. So,
but may I ask, do you invite professors?
So unfortunately, no. It would be nice if we can, but this is only for PhD students. We recently we started opening these parties even for postdocs and scientists, but only within the institute, unfortunately.
Well, I think this is something Taiwanese students could learn. I think they can, organize these kind of events every now and then, I think.
Yes, you're right. You're right. And also with the work-life balance, hopefully, my perspective is that Asian countries are the students from Asian countries tend to overwork. So it would be nice if they can also learn from Western countries in the sense that when weekend comes, they can get the time to rest and focus on themselves. Because in Western countries, we also prioritize mental health. So I think that is something we also need to learn from Western countries.
That's very important. Well, because in my experience, I have been worked in U.S., also in Denmark and Taiwan, also Japan. But then these Asian students, especially Chinese and Japanese, they work all the time. So that's little scary.
Yes, you're right. You're right.
If I go to the lab at night or on weekends, they are always there. Chinese and Japanese students. So
yes. This is not discriminating, just to clarify. It's just that that's really the reality, unfortunately. And so it would be nice if we can, break the stigma about this and learn from what the other countries are doing. So that's why I always emphasize with my fellow students, like, if I see them still working on the weekends, stop working. Let's go out. So let's drink beer or something in Germany. So
Okay. Any questions about life in Germany, and maybe Taiwan and Philippines? So how do you like the weather and the food? It must be very cold there, no?
oh yeah, actually, right now I believe it's still snowing in Munich, so it's very cold. Around it reaches as low as -10 degrees Celsius in my place, and so there's snow, and then the roads are icy. Like if you're not careful enough, you might slip. So most Germans tend to eat. Also, the people in Germany, they tend to eat a lot during winter season because that keeps them hot. So right now, I got a little chubbier because of that. I ate too much during winter.
Okay.
So, but the food and drinks, if you recall, Germany is like the country of beer, and
Right.
I'm I'm living in Munich. That's literally the city of beers in Munich, in Germany. So I learned how to drink beer in large portions, you know.
Oh my
So it's fun. It's fun
Okay.
actually. And if you recall Oktoberfest,
Right. Did you go?
yes,
Okay.
I
It's
went
Munich,
there.
right?
Yes, in Munich, and also in other parts of Germany because it's a nationwide event. So I really recommend people going to Oktoberfest if you have the chance, because it's really celebrating the German culture of drinking beer and beer and beer. So,
Okay. Sounds like fun. I want to ask one more question
yes.
about COVID-19. How the situation in Germany, and does it affect your research?
Actually, no.
Okay.
There's a high percentage actually of the German population fully vaccinated, around 90%.
Okay.
So actually, last December, the German government has already announced that we don't need to wear masks in public transportation and outside
Wow.
anymore.
Okay.
Only if you're going in an indoor establishment, that's when you need to wear a mask. But
Okay.
other than that, the COVID-19 regulations are very relaxed in Germany.
Okay.
And as for me, for instance, I already had 2 boosters already. So vaccines are, what do you call this? You can get vaccines easily in Germany. That's the point. So you can get vaccinated easily, and yeah, regulations are relaxed.
That's good to hear. Okay.
How about in Taiwan, if you don't mind? Fortunately, I'm not well updated.
Well, Taiwan, at the beginning of the COVID-19, Taiwan was, having a zero COVID-19 policy. And it has been very successful that Taiwan was keeping, Corona out of the, country. But then recently, after this Omicron started to coming in, there are more and more infections in positive cases in Taiwan. And so we relaxed the policy. But then by the time this happened, most of the people are vaccinated. So fortunately, not many people become very sick. So at the moment, every day about 10,000 new patients, but almost all of them are not so serious. They only get, like having a cold. So now the policy, well, at the time of zero COVID-19 policy, it was very strict. You have to wear a mask all the time, blah, blah, blah. But then now it's more relaxed. So in outside you don't need to wear a mask, only inside the building. And then
That's
also this quarantine policy is also relaxed. In when you get positive, you have to be quarantined. But then as soon as you get the negative result for the rapid test, you can go out, I think.
Mm.
Mhm.
That's good to hear. Yeah, at least there's improvement now in Taiwan.
Yeah, it's the no. I feel the vaccination is very important.
Yes, you're right.
Okay, time is running out. But is there any questions from audience? I want to spend the remaining 5 minutes for Q&A. Okay. So Poya has a question. Hi, Da. What makes you decide to change your research subject from material physics to astronomy? That's a good question.
Yeah, that's a good question. And that also entails my reason for pursuing astronomy. So, just a short story, hopefully. Back in high school, I joined an astronomy quiz bee. This was done in the Philippines, and I was just engrossed by the pictures that I saw from the books that I was reading. You know, these pictures of galaxies, stars, and nebula, and all sorts of astronomy related things. And then I was just interested in them, and I thought it would be nice to study them in the future. So um after winning the astronomy quiz bee, we won third place, thankfully.
Good.
I decided to pursue astronomy. So in De La Salle University, I pursued physics, and then because of my specialization, I need to focus on material science. Actually, I thought material science is not bad in pursuing, but then NTHU came, and then they advertised their astronomy program. And then my thought there was that it must be a sign because the astronomy program is coming to me.
Yes,
And
good timing.
I
Yes.
thought maybe this is a sign that that my childhood dream is valid and something that I must pursue. So I just gave it a shot, you know, I just applied. There's nothing wrong with applying.
Right.
And then when I got the scholarship and the acceptance from NTHU, I decided to go to astronomy and revisit my childhood dream.
Well, my fellow professors who visited Philippines will be very glad to hear this story, I think. So it was really worth visiting Philippines, I think.
Yes, thank you. Because at that time I was really like, I have already set my mind into pursuing material science, but then they came, and then that's when I started to think twice, you know. And then I think I've pursued the right decision, I think.
Good. Well, I think having fun it's very important thing. So
yes.
Okay. Any other questions? Peter, do you have any more questions?
No, that's fine. Thanks. I found it very helpful.
Okay.
Very interesting.
How about Simon? Do you have any more questions?
I'm curious, did you learn German in Germany?
Good question. Yes.
Yeah, I did.
Hello.
I'm still learning. But it's not required, actually. In Taiwan, they require you to study Mandarin like 4 units, 4 credits a year, just 1 year rather. But in Germany, it's not required. But I always tell everyone, if they visit a country with a different language, it will be helpful to learn their language, to learn how to live and learn their culture, and to make living easier. So that's why I'm still learning German.
But I mean, how about your daily life? Can you survive without German?
Well,
can you order
yes.
beer without German?
Yes. So most young Germans can speak English, but the older people cannot, because
Okay.
somehow they're too old to learn English. So it would still be nice to learn German so that you can talk even to older people, for instance, buying things or like having a chat with the taxi driver. So things like that.
Okay. Okay, thank you, Simon. It's a good question.
Thanks.
How about Albina? Do you have any question to Don?
Hi, Daryl. Long time no see. I would turn on my camera, but my camera is broken on this computer. Yeah. Just a random question then. Do you think it's harder to learn German or is it harder to learn Mandarin? It's different, I guess.
Yeah. Okay. I think they have their pros and cons, but I would choose German over Mandarin only because in Mandarin you need to memorize characters.
You're saying German is harder or
No, German is easier.
easier?
So that's why I choose to learn German more than Mandarin. Yeah.
Okay.
Because in German, the German language, you don't need to memorize the characters. That's almost the alphabet. So
yeah, some words you see it and then you understand meaning.
Yes. There are German words that sound like English words, so that's quite easy. But the grammar, it's a little difficult in German. But in Mandarin, it's more straightforward. So I think there's a difference.
Okay. How about Tom? Do you have any question to Don? Maybe not. Okay. Is there anyone else have a final question? Oh, okay. Tom is typing. Hi, Dad. Do you need to take some courses in Germany? How is academic life in Germany? Oh, that's a good question.
Yeah, it's okay. My program is quite interesting because our courses are only 1 week long.
Okay.
And then we only need to take 7 out of 9 to graduate. Okay. So that's like one of the requirements for graduation. So the courses, as I said, are 1 week. So they're very intensive. And they focus on just one topic in astronomy or astrophysics.
Okay.
We at the start of our year, however, like in our first year, we needed to take what do you call this? Basics of astronomy course. That's like 1 semester, and then we need to pass the test. If you pass it, then you're fine. Then because that's required in graduation. So I would say academic life is very minor in my case. I'm mostly doing research. So
okay. Well, that's an interesting system, and it's good, I think, to focus on one subject for 1 week. Then you can focus on one subject.
In plus, Taiwan, we don't have exams.
Oh, okay. So that's easier. In Taiwan, it's usually the semester is 18 weeks long, and then we have one class at once a week. We have a class, so we need to take 18 classes, and then that's much longer. 1 week, you mean 5 days, right?
Yes.
So that's much longer. Okay, thank you, Tom, for a very good question. Okay, so it's about time to stop. I want to thank you, Dar, for sharing your experiences. It was very interesting, informative.
Thank you,
and then I also want to thank everyone for joining in this schedule. So, and then also everyone asked very good questions, so I appreciate it. And then this Future Learn course will continue, so please stay tuned. And then in February, we have another live session inviting Albina. Albina is actually here. Albina is the next guest in live session in February. Albina is from Brunei, but she also got PhD in UK. And then also she's working in Taiwan, so we can probably hear very interesting stories. So if you have time, please join us in February again with the live session. Okay, then thank you very much again, everyone. And then hopefully see you in February. Okay, thank you. We're gonna finish here. Thank you, Peter, Albina, Simon, Tetsuya-san, Boya, and Tom, and then especially Da. Okay, thank you. See you next time.